So, we have been looking at projection valued measures. So, if you have a locally compact Hausdorff space omega and sigma algebra of subsets of omega, we define what is meant by a projection valued measure. Just for the definition, we do not need omega to be locally compact, any set will do. But we also define what is meant by a regular projection valued measures, which means that those measures we get P, U, V are regular, right. So, that is where the locally compact Hausdorff topology is needed, therefore, regular to make sense. So, the way we came to projection valued measures was via continuous functional calculus, which got extended to L infinity functional calculus, and we looked at the image of indicator functions, right, characteristic functions of subsets of the spectrum, and that gave us projections. And then we rephrased it as a definition, abstract definition of projection valued measures, and we are trying to define the L infinity functional calculus. Okay. So, in the last class we defined what is meant by the integral of a bounded function against a projection valued measure. We will quickly review that and then go to the theorem we stated in the last class. Okay. All right. So, let us start. So, I had omega f. So, omega can be a set or a locally compact Hausdorff space, and we had projection valued measure from script f, that is the sigma algebra, right, to let us say bounded operators on a Hilbert space H, right. And all these things, all P E were projections, right. So, P E was equal to P E star. So, orthogonal projections, self adjoint projections, and if we have something like this, we defined and if I have a bounded function f, bounded measurable function, we defined integral of f dp, right. Okay. So, how did we do this? We did this by well, one could develop the usual integration starting from simple functions and then going ahead, but we were able to do this in one go by taking vectors u and v and defining those measures, right. So, we defined measures P u v E equal to. So, this is a quick review of what we did. I am not going to prove any of this in detail. So, this was a complex measure. Well, regular if we have a locally compact Hausdorff, we assume that. Okay. In our construction, this was always regular. Remember, from continuous functional calculus, we defined those measures mu u v, right. Those measures were regular because they came from Riesz representation theorem and so on. Okay. All right, and from here we defined. So, so this was an operator, right. So, integral of f with respect to the projection valued measure p was an operator. How did we define that? So, integral of f dp. So, this operator acting on a vector u, inner product with v. So, if I tell you what this is, that sort of defines this operator, right. So, this was integral over omega f d p u v, right. d p u v, p u v is the measure given by this, which is a complex regular measure, and the right hand side actually was a sesquilinear form which was bounded, and so there is an operator, right. That is what we called integral over omega f dp, right. So, this is a notation. Okay. We sometimes denote it also by T sub f, right. So, we have seen that before. The point here we proved was that if Fn converged to f in the supremum norm, then integral of f Fn dp converge to integral of f dp in the operator norm, right, in the operator norm. Okay. So, that is like uniform convergence implies convergence of Riemann integral and so on, right. So, it is very similar to that, and if you recall, we had an extra 4 in the bound for the operator. So, keep that also in mind, it will disappear as we go ahead. Okay. So, but at least for the time being this is more than enough. Okay. So, then we wrote down the theorem. Okay. So, if P is an H project. So, H is simply the Hilbert space on which P is taking values. So, projections are acting on the Hilbert space H. P is a H projection valued measure on omega f, then the map f going to integral over omega f dp. So, this is a map from bounded measurable from. So, let me write down that from b omega. So, b omega, remember the b is the usual b. So, that is the bounded functions on omega. So, bounded Borel measurable functions on omega, from b omega into bounded operators on the Hilbert space H, right. Well, the map from b omega into bf H is a star homomorphism. So, which means it is an algebra map. So, f times g will go to integral of f dp times integral of g tp, and the star, it preserves star. So, f bar will have to go to the adjoint of the integral of f dp, right. So, the corresponding operator. Okay. So, that is what we will prove first. So, starting from the abstract definition of projection valued measures, we can define L infinity functional calculus. Okay. Essentially, that is what we are saying. Okay. And now then we will connect it to whatever we have been doing, that commutative C-star algebras and so on, and essentially that would be the statement of spectral theorem in various forms. Okay. So, we will see various forms. Okay. So, let us check this. So, we will. So, keep in mind that the integral of f dp can be written as the limit of integral of fn dp, where fn's are simple functions converging uniformly to f, right. So, many of these properties, that it is an algebra map, it preserves stars, etc., it is enough to prove for simple functions, because we can take limits, right. So, we will check the star homomorphism property, of this map. Okay. So, what is the map? F going to integral over omega f dp. So, remember that this is simply a symbol which gives me an operator, right. So, so we will check that the star homomorphism of this map on simple functions. Right, because once we prove it for simple functions, you can take the limit, and then it will be done for all functions, right. Okay. So, suppose, so first let us prove that it is a homomorphism, that is an algebra map. So, f times g will have to go to the corresponding product, right, that is integral over omega f dp times integral over omega g dp, right. So, suppose f and g are simple functions. Okay, which means that I can write f as summation let us say Cj chi Ej, right, j equal to 1 to let us put an m here, and I have the other function g, which is summation k equal to 1 to m dk chi fk, let us say, right, where Ej, fk, these are all in my sigma algebra, right. So, that is when this becomes a measurable simple function, right. So, you take f and g simple functions, and we know how the integral of f and integral of g are, right. So, let us before that let us see what is f g, then okay. So, then f times g. So, what is f times g? Well, you multiply these two, right. So, you will get the double sum j equal to 1 to n, k equal to 1 to m. I will have c j d k chi e j times chi f k, right. So, you are simply multiplying them, but what is chi e j times chi f k? These are indicator functions. So, if I multiply two indicator function, it is the indicator of the intersection of those sets. So, this is simply summation j equal to 1 to n, summation k equal to 1 to m, c j d k chi e j intersection f k, right. Okay. So, f g is of course another simple function which is given in this form, and now we can integrate, right. So, integral of f times g dp. I want to show that this is actually the integral of f times integral of g, right. That is what you mean by an algebra homomorphism. Well, what is this? By definition, this would be you, because it is a simple function and so on, we have already seen this, right. We simply integrate term by term chi e j intersection f k, that is, if I integrate that with respect to dp, I am going to get the projection of e j intersection f k, right. So, this is summation j equal to 1 to n, summation k equal to 1 to m, c j d k and integral of chi e j f k, which is projection of e j intersected with f k, right. So, keep in mind that if I have a indicator function, this is simply P, right. So, that is that follows from the definition we have seen that. But P is a projection valued measure. So, what would be P E j intersection F k? That is the product, right. So, that is the product of E j intersected times P F k, P F k, right. So, now if you compare with this, you see that instead of chi e j and chi f k, I have p e j and p f k. So, it is the product of two such things, right. So, this is simply summation j equal to 1 to n, c j p e j, right, that operator times summation k equal to 1 to m d k p f k, this operator, right. When you multiply these two operator, you will get what is there, but each of them you know what it is, right, because f is given by this simple function. So, that is integral of f dp would be whatever is here, right. Similarly, this is integral of g dp, right. So, this is integral over omega f dp times integral over omega g dp, right. So, that proves that the homomorphism property for simple functions. Okay. So, one has to prove it for all functions by taking appropriate limits. Okay. So, this is not difficult. So, but let us just make sure that this is fine. Now, if I take two arbitrary functions which are bounded. So, if I take f comma g in bounded functions on omega, bounded measurable functions on omega, then I know that there are simple functions converging to f and g uniformly, right. So, there exists sequence f n and g n of simple functions, okay, such that f n and g n will converge to f and g respectively, right, in the L infinity norm. So, I will have f minus f n, the supremum norm goes to 0, right, and g minus g n, supremum norm goes to 0, right. But f n and g n are simple functions, and we have proved some things for simple functions already, right. So, we can use that. So, let us do that. Well, okay. So, maybe one more step, since so it also follows that. So, because f n converges to f, g n converges to g, and these are all uniform convergence. So, they are all bounded, right. If f n converges to f uniformly, f n's are going to be uniformly bounded. Similarly, g n converges to g uniformly and g n's are going to be uniformly bounded, right. So, because of this, it also follows that. So, we also have Fn Gn. So, Fn times Gn are these are simple functions, right. So, Fn times Gns will go to F times G, right, in the L infinity norm, right, in the supremum norm, in the supremum norm, that is Fn Gn minus F times G, the L infinity norm goes to 0, right. Now, let us recall the basic estimate we had for these operators integral over omega f dp, that is bounded by 4 times the L infinity norm of f, right. So, if some convergence happens in the L infinity norm, there will be convergence in the operator norm, right. So, from here Fn Gn converging to Fg in the L infinity norm should imply integral of Fn Gn dp converging to integral over Fg dp in the operator norm, right. So, let us write down that, hence integral of Fn times Gn dp minus integral over omega Fg dp. Okay. So, the L infinity sorry the operator norm, right. So, well, this is nothing but integral over omega Fn Gn minus Fg dp because of the linearity and so on, and then apply whatever estimate we saw earlier, that it is less than or equal to 4 times the L infinity norm of whatever is there in the integral, right. So, this is less than or equal to 4 times Fn Gn minus Fg infinity, right. But Fn Gn converges to Fg in the supremum norm, right, in the L infinity norm. So, this goes to 0. Okay. So, Fn Gn and its integral. So, this sequence of operators converges to this operator in the operator norm. Okay. But since now we use whatever we have just proved, right, Fn and Gn are simple functions. So, since Fn and Gn are simple and we check the homomorphism property for simple functions. So, we simply integrate and see, right. So, integral of Fn Gn dp is equal to integral of omega Fn dp, right, times integral over omega Gn dp, right, because the homomorphism property is true for simple functions. Okay. So, now I know that this has to converge to integral over omega f g dp in the operator norm, right. What happens to the right hand side of this? I have this sequence converging to integral of f dp again in the operator norm, right. Similarly, this converges to integral over omega g dp in the operator norm, right. So, I have two sequence of operators, let us say Tn and Sn. Tn converges to T in the operator norm, Sn converges to S in the operator norm. So, Tn times Sn will have to converge to Ts, right. So, that is a trivial exercise. Tn converges to T in the operator norm and Sn converges to S in the operator norm, then the product Tn Sn converges to Ts in the operator norm again. Okay. So, if I look at whatever is here, this portion converges to the product of those integrals, right, integral f dp and integral g dp, but on the left hand side I know that it converges to integral of f g dp, right. So, hence integral over omega f g dp will have to be equal to integral over omega f dp, which is one operator, times the other operator, which is g dp. Okay. So, that this proves the homomorphism property, right. So, algebra map. Okay. So, let us go back to the theorem. What we want to prove is if P is a projection valued measure, the map f going to integral f dp, right, this map from the bounded functions into the bounded operators on the Hilbert space H is a star homomorphism. We have just proved that it is a homomorphism. Linearity is trivial, we have already seen that. Okay. So, it is an algebra map. Now, what remains is that we need to check the star property, right. So, remains to check that integral over omega f dp, the adjoint of this operator should be, you take adjoint of f which is the complex conjugate of f and look at the image, right. So, this is equal to integral over omega f bar dp, right. So, this is what you want to show. Okay. So, we can check this again for simple functions easily. So, start with simple functions, and take limit, right. That is what we did in the case of homomorphism property, and the same works here. Okay. For simple functions this is easy. So, let us do that. So, take f to be a simple function, take f to be a simple function. Okay. So, how does it look like? F is going to look like summation, it is a finite linear combination of indicator functions. So, C j chi e j, j equal to 1 to let us say n. Okay. So, we will it is not necessary to assume e j's are disjoint, you can disjointify them if you want. But what is f bar? F bar is simply going to be summation j equal to 1 to n C j bar chi e j, right. Chi e j bar is chi e j itself, right. So, C j bar, this is how it is. Okay. So, let us look at the star of the corresponding operator. So, integral f dp over omega for this f, right. So, now f is a simple function and this we have already seen, this is summation j equal to 1 to n C j p e j, right. For simple functions that is how it is. So, the hence integral over omega f dp star. So, that is the adjoint of that operator. Well, adjoint, so you have summation j equal to 1 C j which are constants and p e j, these are projections, these are the operator. When I take the star of it, I will get C j bar p e j star, but p e j is a projection, right, it is a self adjoint projection. So, p e j star is p e j itself. So, this is nothing but summation j equal to 1 to n C j bar p e j star, which is summation j equal to 1 to n C j bar p e j, right. But then that the expression for this is clearly equal to, so this is also equal to integral of f bar dp, right, because f bar is this is the expression for f bar, right. Summation j equal to 1 to n C j bar chi e j, and if I integrate against dp I am going to get summation C j bar chi e j becomes the projection p e j, right. So, that is integral over f bar dp, integral of f bar against dp, right. So, that proves that it is a star respecting map, star preserving map on simple functions, right. So, now we take limit as we did earlier. So, if f is a bounded function, so I will write just one or two lines to justify this. There exists f n simple such that the supremum norm of f minus f n goes to 0, right, and consequently we know that. So, this also implies that integral of f n dp over omega minus integral over f dp, the operator norm goes to 0, right, operator norm goes to 0. Now, it is a easy exercise again. So, exercise which you already know, if T n converges to T in the operator norm, then T n star converges to T star, right, in the operator norm. Okay. So, hence, so we can conclude now, hence integral of omega f n dp whole star will have to converge to integral of f dp whole star, right. But then we already know that, but integral over omega f n dp star, this we know is integral over omega f n bar dp, right, because we proved this for star. So, star is preserved when you restrict everything to simple functions, we have already seen this, but this you know that will converge to integral over omega f dp f bar dp, because if f n converges to f in the supremum norm, f n bar will also converge to f in the supremum norm, right. F n bar converges to f bar in the L infinity norm, right, because the norms are actually equal there. But we know that this is converging to integral over f integral of f dp whole star. Okay. So, hence it follows that if I take the adjoint of f dp integral f dp, that is simply you take the complex conjugate and then you integrate, right. So, we have proved that once we have a projection valued measure, we have the L infinity functional calculus, right. So, let me remind you, we started with this projection valued measure, right, and we defined f dp for f bounded functions on let us say omega, and this map. So, from b omega to bounded operators on h, f going to integral over f dp integral over omega f dp is a star homomorphism. Okay. So, it preserves. So, the image is going to be a C star algebra, and we have this to be a star homomorphism between b of omega and b of h. Okay. Now, we can get rid of the 4. So, if you remember, if you recall, we had. So, let me write down 2 more lines to say this. We had the operator norm of f dp less than or equal to 4 times L infinity norm of f, right. Now, we can get rid of the we can get rid of the 4. Well, we can do this directly or by using a theorem. Okay. So, let me take 2 minutes to say that. So, recall the theorem, recall that if I had a algebra homomorphism from let us say script b to script a. What was the script b? This was a Banach star algebra, and script a was a C star algebra with identity. So, unital C star algebra need not be commutative. Okay. We did not need that to be commutative, need not be commutative. Okay. So, if you had phi which is a multiplicative homomorphism. So, it is a star homomorphism is a. So, let me write as a continuous star homomorphism, right. Then its norm was less than or equal to 1, then norm phi is less than or equal to 1. Okay. So, here f going to integral of f dp is a star homomorphism from b of omega, which is bounded functions on omega, to b of h bounded operators on Hilbert space, which is a C star algebra with identity, right. B of omega is a Banach star algebra, it is also a C star algebra. So, we have a star homomorphism which is continuous because that 4 is there. So, it makes it a continuous homomorphism, and so its norm is less than or equal to 1, meaning that 4 disappears. Okay. Hence, integral over omega f dp operator norm is less than or equal to L infinity norm of f. Okay. The 4 disappeared. We can also prove this directly. So, we will stop with that proof. We can prove this directly. So, let us see why. This is a standard argument, you have seen this earlier. So, if t equal to integral over omega f dp, then t star. So, what is t star? So, we have already seen this, the map f going to integral f dp preserves the star operation. So, let me write 2-3 lines and then we will stop. Okay. So, t star is integral over omega f bar dp. So, t star t, well, t star t is the product of these two. So, that is going to be equal to integral over omega mod f square dp, because f into f bar gives me mod f square, right. And now, we can look at the norm of t. So, you look at t star t, let us say v inner product with v. So, this is equal to integral over omega. So, remember this is the function corresponding to t star t, right. So, I will have mod f square d p v v, right, which is less than or equal to L infinity norm f square and norm v square, right, because the total measure of PVV is norm v is less than or equal to norm v square or equal to norm v square, and because t star t is positive and all that, the norm, well, norm t square equal to norm t star t, right. This is where the C star algebra identity is used actually. This is supremum over, because t star t is a positive operator, this is true, this is equal to or less than or equal to L infinity norm of f square, right, because the norm v square is 1. Okay. So, we can stop here. We have just proved that the map f going to integral f dp, where p is a projection valued measure, is a star homomorphism of bounded functions on omega into bounded operators on the Hilbert space H, and this homomorphism has norm less than or equal to 1, right. That is, operator norm of integral of f dp is less than or equal to the supremum norm of f. Okay. So, we will stop here and take off from here in the next lecture. Okay.